Hello everyone, my name is Reimin Chen and I'm a PhD student from Penn State Industrial Engineering. Today, I would like to talk about recurrence network analysis of design quality interactions in additive manufacturing. And this work is done in collaboration with my advisor, Dr. Hui Yang. First, I would like to start with motivation, the big picture. Additive manufacturing, or AM, has been receiving many attentions these days because it provides a unique opportunity to produce metal build with complex geometries layer by layer, directly from the digital design. As you can see from the picture on the left side, after loading the CAD model, the machine spreads one layer of powder material to the bed, and then the laser is used to fuse the powder. Then after one layer is built, then the bed goes down and we print the next layer. However, a higher level of design complexity tends to degrade the quality of final builds and lower the repeatability of the process. As you can see in the picture on the right side, in our experiment at Sim3D, we have built identical parts 7 times with the same machine condition. But looking at the outcome, only 2 out of 7 of them were defect-free. So after we saw those results, we started to ask, what are the problems or what are the factors that are causing those defects? So there are 4 main categories of factors that are causing the defect problems in the parts. The first one is machine environment. For example, you may get different output from different machines. The second one is process parameters. For example, when the laser power is low or when the laser power is low, then we don't have enough energy input. The third one is design parameters. For example, how tall is your build gonna be, how wide the part is gonna be, or what's the orientation you wanna print the build, and those factors will all affect the outcome. And the last one is related to the material. And in this study, we wanna focus on the design quality interaction in AM. So we perform analysis on thin wall structures in this study. Thin wall structures is very important in heat exchanger and lattice structure. We printed 3 parts with different orientations, which is 0, 60, and 90. And there are 25 fins on each base with height different from 0.6 millimeter to 3 millimeter, and the aspect ratio of 0.1. We also employed the standard EOS process path, and the table here shows the hashing distance for each thin wall. After the printing process, we obtain the XCT scan for each thin wall part and get the layer-wise image for each scan based on the layer thickness. As you can see from the CT scan here, we have different types of defects such as improper fusion or shrinkage or porosity. And also from the CT scan, as well as the layer-wise image, we see some of the thinnest wall are not printed because of the resolution. The methodology we're proposed in this study is recurrence network analysis. And before introducing that, I would like to start with the recurrence analysis. The recurrence theorem indicates that the trajectory will eventually reappear at the neighborhood of former states. For example, we have 3 signals here. And after embedding them into a 3D state space, we see a trajectory that is reappearing again and again in this red neighborhood. After the thresholding here, we will obtain a recurrence plot. Here, different patterns, for example, those diagonal lines or squares, or sometimes even butterfly structures, they represent different recurrence behavior in the system. Usually, the diagonal lines represent small scale structures, and the disrupted pattern shows the large scale structures. But the problem is in AM, usually most of our data are 2D images or 3D voxels. Compared to the 1D time series data, a pixel, for example, in this 3D image contains more information. The first one, for example, this pixel that is highlighted in red in the 2D image not only include the X and Y coordinates, but also has the attribute in RGB color. So in this case, if we want to use the recurrence analysis to analyze a image data, it's very hard to handle the data visualization and quantification through the traditional analysis. So in this work, we leverage the network theory to investigate the recurrence behavior of spatial data, further characterize and quantify the spatial characteristics through network statistics. We first need to establish the recurrence network. As I mentioned before, let's take the 2D image as an example. So if we want to calculate the relationship of two pixels P and Q in the 2D image, we need to consider both intensity and distance between them, those two information together. The intensity I and distance D are calculated as shown here on the slide. And note that in the calculation of dpq, we use a Gaussian function here. This indicates that if two pixels are far away from each other, the spatial correlation between them tend to be low. And after calculating the weight, we are able to construct the recurrence network. And for the next step, we do the quantification. So network statistics are established measurement for characterization of the topology and provide useful information for statistical inference and predictive modeling. The table here summarizes the network statistics and their corresponding mathematical equations used in this study. The degree represents the recurrence frequency relative to the pixel. In other words, the distribution of degree shows the recurrence distribution of spatial data. The centrality measurement reveals recurrence patterns between a node and the neighbors. For example, the betweenness centrality quantifies the number of shorted paths that pass through one node, which indicate how many times a node reappears in different patterns. Eigenvector centrality is a measurement of the influence of a node in a network, and pagerank centrality is the variant of it. And the closeness centrality is calculated as the reciprocal of the sum of the shorted paths between the node and all the other node in the network. So in this case, the node with larger closeness centrality is closer to other nodes and indicates a stronger recurrence pattern. So to validate and evaluate our proposed methodology, we start with a simulation study. So here, as you can see, we generate 3 groups of thin walls. The first group shows that the thin walls has edge variations, and the second group indicates that there are pores on the top of the surface, but their locations are different. And the third group shows that we have the pore at the same location, but the different size. So here, let's take the group 3 as an example. So here, as you can see, is the first step is the network visualization. So from the visualization, we can see that the blue cluster represent the powder area, and the yellow nodes correspond to the laser fused layer-wise surface. And the green nodes are related to the transition on the edges here, and which is kind of like a bridge linking the blue cluster and the yellow cluster here. There are the edges. Also, note shown in those red circles are associated with the porosity defect. And we can see that as the size of porosity going up, they become more noticeable. And then also the number of nodes in the cluster increases as the size of pore increases. And this figure here shows the distribution of quantifiers we extract from the 3 networks shown in the previous slide. And after looking at those different distributions, then we start to ask ourselves how we can tell whether those histograms are the same or not. Are they following the distribution? And how we can test that. So here we perform the Mann-Whitney U-test for pairwise comparison between histograms among different simulation cases. This U-test is for comparing whether 2 histograms follows the same distribution or not. And the S here denote the sum of rank assigned to observation from distribution X. And here's an example showing the pairwise comparison between histograms in simulation study group 3. So, and then the statistically significant results are marked bold in the table. So the proposed methodology provides a complete structure, a complete picture of spatial patterns and recurrence behaviors through the network visualization and hypothesis testing. For the simulation study, after simulation study, we select a set of 5 quantifiers, which is degree, between centrality, pagerank centrality, and closeness centrality and eigenvector centrality that are sensitive to both powder area and laser fused area in various cases for the next step. And in the real world case study, we start with image registration, which help to correspond to image by a single coordinate system. Why we want to do that? We want to align all the CT scan to the coordinate system that is provided by the fixed image from the CAD model. So here we use a standard registration process with 4 components, which are similarity matrix, optimizer, moving transformation, and interpolator. So here the similarity matrix is the most important one. Is aimed at evaluating the accuracy of image registration, and is which take both the fixed image F and the moving image M prime after transformation, and then returns a value that measures the similarity between the 2 images. So here the D stands for the mean square differences, and here this D is used to define the similarity matrix between the fixed image and the transformed image. And in this formulation here, the big N represent the number of pixels in each image. FP shows the intensity of pixel P in the fixed image, and M prime P denotes the intensity of pixel P in the transformed image. And then after that, here the gradient descent method is used to iteratively update our transformation T and search for the minimum value of D. And after the registration is done, we extract the region of interest ROI from the register image for the analysis of the next step. So in the real world case study, we extract the features, maximum, minimum quartiles, 3 different quartiles, and then standard deviation, screwness, cortices, and entropy from the selected quantifier for further analysis. So here are some features that we extract from the network quantifiers. So for example, the figure here shows the distribution of Q1, the first quartile, for degree, betweenness centrality, and pagerank centrality, respectively. Note that the distribution here are approximate normal. And for the next step, we perform a ANOVA to study the effect of experimental factors on build quality. Here, the parameters are hashing distance, symbol width, and symbol height that we have in our design. They are associated with the symbol number. So in this case, we reorganize our design parameters into 2 groups. The first one is the orientation, O, which has 3 levels, 0, 60, and 90. And then the second one is called symbol characteristic, C, and which has 21 different levels. Note that this is because the last 4 symbols are not printed because of the resolution of the machine. And the example here shows the ANOVA test, the hypothesis whether the orientation and the symbol characteristic are impacting the feature maximum degree. And the p-values for the symbol characteristic, orientation, and interactions are all approximately 0, which indicates that those 3 factors are all significantly impacting, or they all have significant impacts on maximum of degree. So we perform this 2-way ANOVA on total 45 features, and then we calculate the Hotelling T2 statistics for each symbol as our response for our regression analysis for the next step to quantify the relationship between design complexity and the network features. Note that here we also conduct the square root transformation of the response variable Hotelling T2 to improve the variance stabilization. So significant variables from the regression analysis are summarized in the table here. And note that because our orientation is a categorical variable, which has 3 levels, 0, 60, and 90. So here we did the coding for the orientation variable. So as we can see from the table here, the orientation O, height H with W, and the hashing distance G are important one-way factors with p-values less than 0.05. And it's also worth mentioning that the p-value of beta 4 here for H is larger than the p-value of other coefficient, which indicates that the parameter of height H does not impact the quality of thin walls as much as others. We also observed that most of the two-way interactions, for example, orientation and width, orientation and hashing distance, are significant, thereby impacting the quality significantly. However, the two-way interactions, for example, the orientation 60 and height, which is O1 and H, that is not shown here, and then the width and height and the width and hashing distance do not have impact on the quality because their p-values are greater than 0.05. And in total, the regression model yields the R-squared statistic of 87.12 and the percent, and the adjusted R-squared statistic of 87.08%, which demonstrate that the variation in the response variable are highly correlated with the design parameters. And also the normal QQ plot here illustrate that the normality assumption is valid because the plot approximately follows a straight line. So as a conclusion, we are facing 3 main challenges in our study. The first one is we need to characterize recurrence behaviors and patterns in AM spatial data. Then the second one is we need to think how we can measure and quantify the recurrence features from the recurrence analysis. And then at the end, we want to analyze the relationship between extract features and the quality of AM builds. So in summary, we visualize the complex spatial patterns in AM images that overcomes the Kurzem dimensionality problem in the traditional recurrence plot methodologies. And we leverage the network theory to characterize and quantify the recurrence properties. And at the end, we perform the analysis of experiment to select important features and predict how design complexity impacts network characteristic in each layer of the thermal build. And those are the referencing papers for this study. And if you have any questions, please see our contact information here. And thank you.